All right, so today we are going to talk a new series. So that's why we have a new opening video because we have been finished talking about the microprocessor and the memory part. Now we finally have tried all our best to bring down all the memory latency to just a few cycles. So it would well, as we mentioned before, once you optimize one bottleneck, the bottleneck shift to another one. So it's now the time to talk about the main part, another main part in volume architecture, which is the processor. So I know you have missed this slide a lot, but the reason why we want to talk about this slide again and again is because don't forget the volume architecture, or in general, every computer that we have nowadays, they are composed of memory and processor. And for a processor to process an instruction, it comes from the very beginning that somewhere in the processor, typically a program counter register or an instruction pointer, which directs to a memory location where your instruction stores. And then particularly in your processor, there is a certain logic will interact with that memory address to fetch the instruction that we want to execute. And then once we get the content, we analyze the bit strings that we receive to figure out what kind of operation we want to do. And then we prepare the inputs for this upcoming instruction and then select the correct or appropriate functional units in the processor to execute that and write back the result to somewhere in the processor for future usage. And then once we are done with this whole circle of executing instruction, we are able to advance to another instruction. And sometimes some of the instruction, they would trigger additional memory access to get the data externally from the current content that we have in the processor. Or sometimes we may not like straightforward going to the next instruction because we are interfacing some of the conditions that would require us to jump back or jump forward to another location that is not your next instruction. But no matter what, the beauty of this computer architecture is that whenever your instruction streams are doing different things, your computer, without reconfigure the hardware, it can do different things. So in this sense, you can consider what a microprocessor is. A processor is, in fact, just a collection of functional units. And typically, a general purpose processor would contain instructions that perform logical operations. For example, this would use a lot when we do like if-else statement or the loop condition, because we want to know if this is true or false. Or sometimes we just want to do a very quick comparison or getting some kind of easy zero out, we would try to use this logical operation. And there are also simple arithmetic operations. For example, the straightforward addition, subtraction, or integer operations that can be done really fast. But sometimes we also have complex arithmetic operations like division or multiplications. If you have learned like 140, which a lot of people, I think it's a nightmare for you, but you must spend a lot of time looking at the design of a multiplier or a divisor because they are really complex to design. And as you can imagine, those logic, they are larger and they take more time to execute. And so that would need a separate set of ALU logic to figure that out. And sometimes we want to decide which is the next instruction to go. So that's why we need branch and jump instructions. And the ALUs corresponding to that. And finally, because you need to fetch data from somewhere else, so your processor should have memory operations. But most of the time, our processors, they do a lot of things internally, but they just try to simplify things. So turns out all the processors nowadays, they have some kind of language that they talk to the external world. And that language is called instruction set architecture. So famous examples of instruction set architecture includes Intel AMD's x86, which is the one that you use a lot. But believe it or not, each x86 instruction nowadays later on we will talk about this, is that even though like just have an edit instruction internally, the processor would decompose this edit instruction into several micro operations, which is the real ALU operations and memory operations that the processor will perform. So this instruction set architecture is simply an interfacing language between your processor and the rest of the world. And why do we need this kind of one additional layer of instruction is because the good thing about this is that the instruction right now is just a common interface between hardware and software. And the hardware can use the most effective way to interpret those instructions and doing their own things in their internal hardware logic without letting the software know. So the good thing is that the software can maintain the same set of instructions without being recompiled. So grandfather old programs, they can still work on new processors because the processor internally maintain this abstraction. And any processor support the same instruction set architecture, even though they have different latencies in memory, they have different implementation of instructions, the same program will still run. That's why AMD can also produce x86 instructions. That's why you see a lot of ARM processors, they all come from different vendors. Like Apple is probably now the largest ARM processor producer, as well as like Qualcomm, they also produce ARM processor. And you don't need many different versions of ARM compiler to make it work because they all support the same instruction set architecture. So, and with that, what does that mean is that on top of that, we can leverage the same programming language. So no matter you are using x86 or ARM or MIPS, whatever, you can all program in C, C++, Java, or Python because each layer, they abstract the underlying layer. So this is where we live now, and today we are going to talk about the basic idea about the internal design of the processor. However, before we start, we always, as our tradition, we always want to have some like icebreaker questions. So today is this. All right, like, okay, I saw this, I heard this question seems to be more involved. So what do you guys think? Like, what are the critical or tricky questions that you ever had? No? Okay, Mitchell, what do you have? very tricky conceptual question. Mm. Not a lot of people have heard. Mm-hmm. And some people would try to attempt it, but I guess the real tricky answer was, I don't know. Okay, but what was that question? I forgot. Okay, so you really don't know. It was like something about what if. Okay, what else? What else do you guys ever have? No? How many of you had a coding interview before? Okay, which question did you struggle with, or you ace all of them? So it's a piece of cake that nothing worth talking about. I think one of the harder questions that I had was like it was for a cybersecurity position, but the questions like I had to explain the entire like private connection between like you trying to like say like log into Netflix, like how the cybersecurity connection works, like the whole thing from start to finish. Mm-hmm. And I was like on the second or third step, and I was like, shoot, I know this one by heart after that. Okay. And then I overcomplicated a simple pointer question. Mm. Simple pointer question. What was that about? It was like, imagine you have like three nodes. It's like you have an infinite list of nodes, and I give you like nodes 4, 5, and 6. I want you to get rid of node 5, but you don't know what comes after. Like you don't know how what comes after. You don't know like the start. Like you don't know what the head is or what comes before. So basically, like a list traversal question, and ask you to delete an arbitrary node. Yeah. So then all you have to really do was just make node 4 point. Is it a double A linked list or is not? No, it's just a regular, just one way linked list. Huh. Okay, that's really tricky. Yeah. And then all you have to do was, I felt so foolish when he explained the answer because he explained it to me at the end. I was like, oh wait, that's so genius. But you just have to make node 4 point to the address of like node 5, so that, or no. So if you want to change, so you have node 4, 5, and 6, change node 5. So instead of it having this content, you make it point to the address of node 6. So when node 4 goes to point to node 5, it skips it and goes to node 6. Mm-hmm. So it's pointing to this address. And I was like, oh, that's so simple. And then I was over here like making a temporary node, make it point this way. And I want to hold this information, do a bunch of like the temp swap and all that. And I had to do all that. And right. Then I ended up having like a, what was it, like dangling point or like like yeah. Because now it's lost the link and you have to figure out which one is that. Yeah. Okay. Did you want to say something on the show? No? Anyone else? What? Okay. I hope next summer you guys would, well, before next summer you guys will have a lot of interviews. But you know, like there is one interview question that I specifically against, but a lot of people like to test, is actually this. Like, oh yeah, these are the companies that ever test this question. How to swap two variables without using a temporary variable. Broadcom tested that. SAP tested that. Like every time when I fly to San Jose, before I land, I would see SAP on one of the stadium. And like Qualcomm, okay, I don't think I need to mention where that company is, right? They all test this question: how to swap two variables without using a temporary variable. And in fact, if you're interested, here are like a few tricky C or C++ programming questions that people listed, and apparently swapping two variables is one of the popular ones. And remember, like, okay, so how to swap two variables, the content in two variables without using a third variable? This is actually the right answer that Qualcomm, Broadcom, SAP, they are looking for, right? But let's take a look of the performance of this, right? So here's the code that I wrote. So this pieces of code is a flip array. So the flip array means that I have an array of data and then I want to flip the content. So definitely I would like to do a lot of swapping in place, right, from the tail to the head, right? So this is also one of the popular interview questions if you think about the flip array thing, right? This is actually a question in LeetCode. Okay, So a lot of people, like companies like Qualcomm, they are looking for the second option, like exclusive or swap. And let's take a look of this idea to see if it's better. So right now, to be fair, I run 10 instances for each. And as you can see, the upside is the version using a third variable. And the bottom side is a version without using a third variable, right? And you can see the bottom side is consistently slower, right? So sometimes I feel very surprised why companies like Qualcomm, they keep testing people to write code without using the third variable, because like for performance wise, I don't see any benefit, right? So, but this is actually not very intuitive to a lot of people. Is it intuitive to you? No, right? So, and also like previously, we also tested you about this, right? Like when sorting array, um, uh, um, like why like adding a sort here would increase the performance of the rest pieces of a code. Some people may think about, well, is there anything to, well, especially after you learn the memory hierarchy, you might think, is there anything to do with the memory? But the answer is no, because if you look at the spatial locality before and after sort, there's nothing different. The access pattern is not changed at all. So there must be something else here. And this series of a lecture this week and the following week, we are going to answer all of this question because they are all related to what a processor pipeline looks like today. So let's talk about what a processor is. So the basic idea of the processor is queued an instruction. So based on your reading, based on your understanding, based on the recap I have, what's the life of an instruction from end to end? Like how do we execute an instruction? What's the very first step? Fetch from where? From the memory, right? So we get an instruction from the memory. What's the next?
Load instruction into processor.
And then that's actually the fetch, right? Decode, right? So what does that mean by decode? Transfer the instruction, transfer the instruction to the memory that we have, well, from the memory to the processor that we have done, right? What's the next? What's the next thing? I got this instruction, then? Decode, what does that mean by decode? Load it onto the register file. Okay, so decode is actually doing this. You guys need to do the reading quiz. Indeed. Okay, so the decode means that, first of all, understand what the instruction is doing, right? So then I can set those control signals to figure out which is the right ALU that I should aiming at, right? So for example, without knowing this is an add instruction, without knowing this is a logical operation, I have no idea which ALUs that I should use, right? So this is actually really, really important. And the other thing is that during the next stage, you need to run these instructions for sure. So what are the inputs that this instruction will require? That should be prepared at a time when you decode this instruction, right? So then once we have figured out what instruction we want to do, what instruction is, once we figure out where are the registers that this instruction will access, then what's the next? Yes, right, we execute the instruction. And based on what instruction we have, we will have to do different things. So for example, if it's just arithmetic operations or logical operations, we will use ALUs to perform ALU operations. And if it's a conditional branch, for example, like BNE, jump, this kind of branch instruction that would change the direction of an instruction, at this point, what we need to do is that we have to calculate the effective target address of the instruction that we are going to access next. And the other thing is that a lot of people have the misunderstanding saying that memory instruction only access memory. The answer is no, because don't forget, to get the effective address in the memory to access, you also need to perform arithmetic operations, right? So for example, in x86, we always formulate our memory part as a base address plus offset, and some of them even have shift amount, right? And that's actually require several ALU operations to make it happen. So the address calculation part in memory instruction also require to use a few arithmetic logic unit. And then if it's a memory instruction, you probably want to access the memory. And for memory access, it's probably read or write, depending on what you want to do. And if it's a load instruction, then, or say a read instruction, you need to present the read value inside a target register. And even for arithmetic operations, you also need to temporarily store your result into a certain register. And as you already learned from your assignment 2, it typically a variable, temporary variable or local variable, they will represent a target register here, right? So those target registers are where you have to, or this is the time when we are going to update that. And if it's a branch instruction, conditional branch instruction, this is also the time to update your PC to the branch target if we decided to take the branch. Otherwise, we would just advance to the next instruction. And so now, based on this understanding, right, since the first step we have is to access the instruction memory, right? So how we access memory nowadays is that we don't directly interact with them. We have the cache. So cache is the first part, right? And then who to fetch from the cache is actually the instruction fetch unit. And the instruction fetch unit, knowing where to fetch from a specific register called program counter. So that's why we need a program counter. And you should have an instruction decode unit to figure out what to have after you fetch the instruction. And then you have a set of registers provide the inputs for the following operations or the outputs for the following operation. So, and then finally, these registers, they would have a path, a channel to talk to these functional units that we have. And depending on the operation, so for example, if you have memory operation, you have to do address generation and then perform data access with the cache again. For the memory operation, you have to put your result back to your register if it's a read. For ALU operation, you also need to put your result back to a register value if you need. And for arithmetic operations, you also have to do this. And the only thing that doesn't need to update a value register, general purpose register, is actually branch and jump. However, they do have something that need to update. That's actually the program counter. So this whole thing is basically a design of the processor. So based on what you have to learn, what you have learned in CS140, the easiest way to make this processor work is that, first of all, I should have a clock which signals the processor when to receive and execute an instruction. And the most naive design would say the single clock would allow the instruction to run from the very beginning to the end. And then once I finish the whole instruction, the clock signal changes again, and I fetch the next instruction. So you can imagine this is the timing diagram we have. And you can imagine each of this is actually a clock. So you can consider now, each clock cycle, you have to be make the clock cycle as long as the longest amount of operations that you need for an instruction. So from a lot of understanding, this is not going to be very efficient. So most modern processors, they all contain this design called pipelining to optimize for the performance. So the basic idea of pipelining is pretty much like we separate your circuits into several different parts. And every clock cycle, instead of going through the complete data path for executing an instruction, we only do it part by part, step by step. So this is pretty much like what you would experience every day during the lunchtime when you visit Subway or Panda Express. So for example, for Panda Express, right? Sorry, not Panda Express, because I haven't been to some Panda Express for quite a while, so I don't know what they do now. But like for Subways, for example, right? Typically, there will be several attendees in Subway, right? And then the first people would ask you like, oh, what kind of bread, right? Do you want it to be toasted or not, right? So for example, once you're done with the selection, like me, typically flatbread, right? And then this person no more talk to you, right? You are moved to the next person. And in the meantime, this person would talk to another customer, right? And then you can continue with, you probably need to wait for the oven to finish, and then they will ask you what kind of protein, right? For example, chicken breast. And now you're done. What kind of like vegetables, right? Like lettuce, tomato, cucumber. That's what I typically would get. Do you want mayonnaise, right? That's also what I would get. Okay, done. And then you go to the register, right? So this is like a pipeline stage. And every time you only interact with one person with small amount of stuff. But if you go to a coffee shop like Cups, how many of you know that one? The one near the bear, right? There is a small coffee shop, right? There's only one people there, one person there. She or him they do the whole thing, right? There's no other people, so the throughput is really bad, right? So the idea of pipelining is pretty much like Subway. Instead of a clock cycle finish an instruction, a clock cycle will only finish part of the work. So with that, what's different is that now we separated the processor's task into several different stages. Like here, we have 5 different stages. And between each stage, we have a pipeline register to save the current progress from the previous stage. And then what happened is that every cycle, I release the content in the pipeline register to the circuit that I have. So now, the first cycle, when I execute the first instruction, instead of having the instruction go all the way to the end, you only need to finish, for example, this part of the work. And then in the next cycle, I release the current content, which I stored from the last cycle in the pipeline register to the next stage, so that the next stage can continue from the work where we left over and then work on the second part of the work. And then in the meantime, the previous circuit that occupied by the first instruction are freed up for the other instruction. So continuously, when the cycle time advances, you can imagine this processor is now filled with different instructions. They all work on different parts of the processor circuit with different progress. And a few good things about this. First of all, now your cycle time is only need to be as long as the stage that takes the longest amount of time instead of the whole data path. So your cycle time could be a lot faster than it used to be. And the other thing is that your throughput will be a lot better. If you cannot really get the idea of why the throughput is a lot better, let's take a look at this pipeline diagram. So with this, right, you can imagine for the same stream of instruction, I can now, each cycle, I only need to finish one stage at a time. And the good thing about is that, remember, this cycle time is now shorter. And each cycle, because I'm always finishing an instruction. So the amount of instruction being finished, well, so every cycle, I'm still finishing almost the same amount of instruction. However, the cycle time is a lot shorter, meaning that my performance will be a lot better. So this is the basic concept about pipelining design. So if we say the previous case where we use one cycle to execute one instruction, the CPI equals to 1. The pipeline also gives you CPI equal to 1 because every cycle I'm finishing one instruction. But to be aware is that here the cycle time is only just like a quarter or even shorter than what it used to be, which gives us a large improvement of the performance. Remember, the performance equal to instruction count times CPI times cycle time. And here, instruction count remains the same, CPI remains the same, your cycle time gets a lot shorter, so your performance is a lot shorter, is a lot better. Now, given here we have the concept of pipelining, is it really as ideal as we would imagine? All right, let's take a look. Okay, so most of you think the answer is B. So why don't we take a chance, because sometimes your two may be different from others too. So why don't we discuss with others? Oops, sorry. Go back. All right, let's take a look. So now more of you think the answer is B. Okay, so there are two that we cannot finish back to back. What are the two pairs that you guys have in mind? Okay, what do you have?
I was thinking
2 and 3 and 4 and 5. Why?
because 3 depends on what's in ECX, since we have to finish for 2 to finish for that.
Mm-hmm.
And then
2 and uh, 2 and 3.
yeah, and then 5 depends on 4 having RDI, like at 4 being at its RDI.
Okay. Okay. What else? Any other thoughts? Any other thoughts? Any other thoughts? Okay, let's take a look, right? So for this kind of question, you cannot just think. Sometimes you have to schedule it, right? Like, a lot of cases we saw this is going to work, but without really doing some simulation, it's not easy to tell that. So the same thing happened here, right? So first of all, for the first instruction, right, there are a few things that we need to do, but it's always the case that we have to fetch it, and then we have to decode it. And while you are decoding the first instruction, it's definitely safe to fetch the second instruction. Now, when we execute the first instruction, it's also reasonable that we decode the second instruction and fetch the third. Now, when we want to write back the first instruction, and then we are executing the second instruction, but by executing here, because this instruction is a memory instruction, so you know that we need to do address generation first, and then we can do memory access. And in the meantime, the third instruction can be decoded. We are fetching the fourth instruction. Now, for the next cycle, is it safe to execute the third instruction? No, right? Because why? Because the ECX hasn't been accessed from the memory yet, right? Okay, is that all good? Is that the only issue here? So right now you are talking about 2 and 3, right? Is that the only issue here? So this means that I'm going to add ECX, EAX, and put it back in EAX, right? So I need to have the value of EAX as well. And the thing is, like, there's also another instruction. They want to access EAX. Which one should go first? They are doing this in parallel, right? So, like, this is pretty much the case. I don't know if it happens to you all the time, right? Like I'm living in a place with a single laundry, right? My roommate and I, sometimes we would occasionally meet outside the laundry room. Hi, right? What is that, right? It's pretty much like, okay, everyone wants EAX. I want it, you want it, right? What happened, right? So that's actually some kind of hardware resource conflict, right? So the answer is that 1 and 3 actually have an issue. And without like plotting this pipeline diagram, it's difficult for you to figure that out, right? And the other thing is, a lot of you already identified the memory content, between ECX here is not ready yet. And the other thing that we also want to say about, right? Even for 2 and 4, there's also another issue, right? 2 and 5 actually. You cannot actually fetch the fifth here because both of them, right? Remember the hardware diagram that we have, right? Have to access this cache, right? So we cannot have the cache served for both, right? So this is actually not going to work because of that, right? So this is an issue, right? And the other thing, as many of you mentioned, ECX is not ready when we want to start executing EX, right? So in fact, simply here, 3 pairs already having trouble, right? 1 and 3, 2 and 3, 2 and 5, right? And there's actually more, right? So for example, we try to advance more. Now, okay, 2 and 3, right? They both want to finish at the same stage, but we only have this part of the circuit, right? And they have different lengths of progress to finish. This is not going to work either, right? So, and keep going, right? So like here, again, we have this dependency issue. So 4 and 5, some of you already mentioned, right? And finally, now I have this J and E, right? Here, it could go back or it could go forward, right? So I cannot actually keep fetching here, right? So if you don't continuously fetching, you won't be able to output back to back, right? So what turns out is that, in fact, 1 and 2, 1 and 2 doesn't have the issue, but 1 and 3, 2 and 3, 3 and 3 and 3 and 3 doesn't have it. 2 and 4, 3 and who is that? 5 and 6. Well, yeah, 5 and 6 and 6 and 7, they all have this kind of issues, right? So the answer is actually 5 pairs of them, right? So in reality, it's so difficult to achieve the so-called CPI equal to 1 if the hardware doesn't do anything, right? So the takeaway here is that right now on the hardware side, we have made everything pipelined, and the theoretical CPI should be the same as a single cycle design, and we can take advantage of the like reduced cycle time. However, this is very difficult because we have pipeline hazards. So there are 3 types of pipeline hazards. The 3 types, they are in these 3 things. First of all, the first type is called structural hazards. Structural hazard means the case where I have 2 instructions, they are competing the same hardware unit. So like the case that I said, if and my roommate, we all want to use the laundry room, right? There is an issue here, right? So this is called structural hazard. And the second thing is called control hazard. So like the PC may be changed, the program counter may be changed by an instruction in a pipeline. So for example, without this outcome being resolved, I have no idea where is my next instruction, right? So this is pretty much like sometimes there is a decision we have to make before we can proceed, right? So like yesterday, I was watching a baseball game between Padres and Giants, and there was one. Apparently, I think he must be a Giant fan. He tried to interrupt. He tried to grab the ball, and apparently, you saw that one, right?
I didn't see the game, but I saw people talking about it.
Yeah, and the thing is like that guy is apparently a Giant fan, and I was like, and then for some reason, the New York side of the MLB, they decided to take this play under review, and it was originally a home run on our side, and now it was taken back, and it's even worse because I thought at least you should give us like a 2-base hit, but turns out they give it like an out, which I don't think Ramos ever catch the ball at some point. But anyway, but why am I talking about this? Because during this period of time, right, before the resolution was out, you don't know if we are going to continue with 1 out or no out, right? So, and without that, we will have to do things differently, right? So this is like control hazard. And the other thing is called data hazard. That's actually something that a lot of you have already identified. Sometimes I just have to, the result is not coming out yet, right? So I can only wait there, right? So that's 3 types of hazard that we have. So now look at this. From what we had in the very beginning, how many of those are data hazards? All right, let's take a look. So the initial vote, well, pretty diverse. So why don't you guys discuss with others and let's take a look after that. All right, let's take a look. Okay, after discussion, slightly more of you think the answer is 2. Okay, so in fact, the answer is 2, right? What are the 2? So remember, what's the definition of data hazard? One instruction is waiting for the outcome as its input from the other instruction, right? And that outcome hasn't been produced yet. So based on that, right? So this is definitely one case. Well, sorry, this is definitely one case because this one is right now not finishing yet, right? And the other case we will see is also this one, right? So the thing is that because we haven't finished our DI, so EX won't be able to get it, right? So both are the cases where we are going to see data hazard, right? So, but others, if we take a look, there is structural hazard because this one is actually competing functional units. And this one is also competing the access of the same register file. So this is also data hazard. Structural hazard, not data hazard. And for this one, because we don't know where is the next instruction to go, so it's considered as control hazard. So now, based on your understanding about these 3 types of hazards, why this pieces of a code on the right hand side is not as performing as the other version? All right, let's take a look. Okay, so 3 answers, they are all popular. So why don't you guys talk to each other, try to convince others that you are right, or maybe figure out from others why you think differently. All right, let's take a look. What do you guys think afterwards? So now 83% of you think the answer is B. And in fact, the answer is B, but why? Can someone try to let me know why you think that way after your discussion? Okay.
I think wouldn't the A in the second line depend on the A from the first one?
The second line, depending on.
The A in the first one.
Okay, so wait, the second depend on the A?
The second A from the first one.
The first A, the second A what?
Like doing the instruction depends on the A from the first one.
Is this one depending on the first one?
I don't think so.
Okay, so you are saying this one is depending on this one.
Yeah.
And
Well, that was an effective term. But I think then that's a data hack, right? So,
okay, so this one is depending on this one. What else? So this one is also depending on this one, right? So in fact, these 3 lines of code, they have to be executed in serial, and without the first being written back to a register value, you cannot continue, right? But let's take a look at the first one. So first of all, this line of code, is it depending on the first line of code? It's actually not, right? The first line of code is not the input. So only this one is depending on this, right? So you don't have that many data dependencies. So later on, you will know, without those data dependencies, these instructions, they are more likely to be executed back to back. So that's why the left-hand side actually have better performance. So a lot of like old programmer, they believe the right-hand side of code is faster. But they must be grandfather old, I bet. And the reason is because pipeline processor is a concept starting from early 90s. So that's where a lot of us haven't been born, right? And a lot of people who born or even work before 90s, they think, well, processor, they execute 1 instruction per cycle, so the right-hand side is probably faster because you don't need to put stuff in the register, which saves the instruction count. However, in fact, this part, because you have more parallelism, you are allowed to pipeline stuff better, you don't have data hazard. So it's actually running faster, right? So if someone tell you this one is faster, you can easily tell is this guy or this person must be super old, like a grandfather. Otherwise, it's an idiot or has no knowledge about computer architecture, right? So I don't know why those companies like to test this. They probably want to test you how good you are in the usage of pointer, but in reality, never try to write these pieces of code. First of all, difficult to understand. Second, it's not performing, right? So a lot of you might be thinking about, okay, I keep telling you code that are more difficult to understand. But my standing point is that I only write ugly code or hard to understand code if I can get significant performance benefits. However, like this case, I really would like to have you guys all use a temporary variable here because it's actually faster, easier to understand. Why don't we do that? You know, like if any principle in software engineering or algorithm class would make the performance better, I would go for it. But unfortunately, a lot of things that you learn from both classes, they are actually make the program slower. So that's why you see I have a lot of things to talk about on them, but doesn't mean that I'm against them, just because in terms of performance, which is really relevant to the cost of operation, you don't want your code to like that. All right. Okay, so the second takeaway from this lecture is that we have 3 types of pipeline hazards preventing us from reaching the theoretical CPIs. They are structural hazard, control hazard, and data hazard. So what happens if we what to do if we meet a pipeline hazard? So the universal solution that will solve all the issue is just stall, just wait, right? You know, like sometimes, like if you have an issue, just wait, right? It will automatically resolve. For example, like, okay, if I bomb my midterm, right, and I feel really bad, what to do? No worries. 3 more weeks, you are done with the quarter, and the issue is resolved, right? So sometimes just wait. No, I'm just kidding. But the thing is, that, you know, time will heal. The same thing as pipeline hazard is like, okay, for this situation, right? Right now, we have the issue that this instruction cannot be decoded because the first instruction hasn't finished. Then what if we just let the second instruction wait a little bit? By wait a little bit is that don't make any progress here, even though I know you did something in instruction decode. Don't trust it and don't move forward. This is called stall. And the instruction after also does the same thing. So this is typically how we implement stalls. It's just that the instruction should be waiting, stay on the same stage, doing the same thing again, next cycle. Right? So for example, if you didn't do well in this class and you still need a credit, take it again. Right? So the same thing here, right? Like, okay, if I cannot decode with the right content, let's do it again. Right? So that's pretty much how we implement stall, right? Like here, right, I still cannot decode because so right now, the first time I cannot decode because I have the EX issue. But right now I cannot decode because I have the ECX issue, right? So now, because of that, I have to stay and decode 1 more, and right now I can finally get my right content in a register to work on the next stage, right? So this is actually stalls, right? But as you can see, for these pieces of code, if I want to implement stalls, then I would actually need 4 additional cycles to execute this instruction, which make the benefit of pipeline not really attractive, right? So in fact, we have to figure out things that's not waiting. We have to aggressively think about how can we improve it. Like for example, right now, if you know I didn't do well in my midterm, you will think about something else that I should do instead of just waiting for the quarter to finish, right? So like for structural hazard, what do we have to do? So here's the thing, thinking about the source, right? So it's really important when you meet an issue, figure out what's the cause of that, right? For example, if I didn't do well in the midterm, why is that, right? And then try to figure out how to address that. And the same thing, the main reason why we have structural hazard is because we have 2 instructions competing the same hardware resource. As I said, if I and my roommate are keep competing with the laundry room, and it causes us to have like really bad relationship, right? How to fix that, right? So an easy enough thought about that is, well, why we change the schedule, right? So like what we typically do right now is that I would do my laundry on Sunday, and he would do his laundry on Fridays. So it turns out that we would never do laundries on the same day, right? So same thing here, right? There should be an agreement on these two instructions that competing the same resource regarding what's the order first. And the other thing is that fortunately, for example, like register file access, it's pretty fast. So the easiest thing to do is that we can, and like the laundry, right? Like the laundry room, you have two parts. One is the washer, the other is the dryer, right? So, or even like sometimes I can tell my roommate that, okay, let me do the laundry first, let me do the washer first, and then once I'm done with the washer, you can use the washer, right? So the same thing here is for the register part, I can have the earlier instruction perform the update at the first half of the cycle because register update is really fast. So one thing that is possibly doing is that within the same cycle, it's good enough to do both read and write together. But the first cycle, it can do write, and the second cycle, you can do read. And there's a reason for that. So first of all, we want to do write early, read later, because typically the return result will be consumed by a later instruction. So if you can do the write first, all other instructions that would rely on that pieces of data would be able to continue. And the other thing, if both are accessing the same address, the same register file, it's better to write it back first anyway, because whatever the later instruction read doesn't make sense if the earlier value hasn't been written back yet. So based on that philosophy, you should always try to write first and then read later. And so here's the agreement. Whenever there is a conflict between write and read of a register, write goes first and then read later. So, and they can be done in the same cycle. So with that being revised, right? Now our new pipeline will be something like this. Okay, so the second thing that we can talk about is we do have the issue of both data access and instruction memory access. They all want to access this L1 cache, right? So how to address that issue? And in fact, you guys have seen that design a lot. So the answer is pretty simple. We just made two separate cache units at the L1, right? Remember, when you profile the cache configuration, there's I cache, there's also D cache, right? For our assignment, we focus a lot on a D cache because the cache, the data access behavior is something the programmer can change. And the other thing is that for the instruction, as we talked about before, it has great spatial locality and temporal locality. So typically, there's not really a lot of things that you need to optimize for the instruction cache because the hit rate of instruction cache is typically 99% of the time, right? So that's why we don't focus on instruction cache a lot because they are designed, their locality is actually pretty superior and nothing to improve, right? But why we have two separate pieces of cache? Because we want to avoid the structural hazard between instruction access and data access. So now you will know the answer why for the L2 we only have one, L3 we only have one unit, but for L1 there is always an instruction L1 and data L1, and this is almost universal to all processes right now because we are oftentimes have to deal with the case that instruction access and data access, they are at the same time. So now let's give a quick update about the pipeline we have. As we show in this figure, notice this, instruction access goes to instruction cache, data access goes to data cache. Question?
Yeah, just wanted to confirm something about the L2 cache. There's the split L1 cache, but we don't need a split L2 cache because the instruction L1 cache is already super optimized. So since the hit rate's so high, we don't need to also split.
And also, you don't directly interact. The processor never directly interact with the L2. Right? So it's the L1 interact with the L2, right? And if both the L1 and if both instruction L1 cache and data L1 cache, they are optimized in a way like, for example, if you have 90% of the hit rate, then the case where both of them need to access L2 is actually rare, right? So, I mean, you can definitely have a split L2 cache, but that won't give you too much benefit. Question?
Is this like physically like allocated, or is it like you choose how much cache?
No, it's actually physically separated. And the reason why they made it physically separated is also interesting, because for the instruction cache, the processor never modified the instructions, right? Like from the von Neumann architecture model, we always just fetch the instructions, right? So the instruction cache is actually read-only. And with that, when you implement this hardware, like if you know how to write Verilog, you know even the declaration of the functional units is different, because like this one, you have to use rewrite port, but this one, you only need the read port, right? Make the cache design simplified, and like in hardware design, every penny counts. So they won't make it reconfigurable because it's too complicated. Question?
Something like this would be unnecessary, something like the hardware architecture, right?
Say again?
If you were using the Harvard architecture instead of the von Neumann, this is an optimization that would be unnecessary, right? Because instruction data are already separated.
Instruction data already separated, so
you wouldn't need like a split L1 cache because is that right?
So you are talking about like if you have a Harvard machine. Well, because you are naturally separated them, right? Okay, but who is implementing that, right? Anything else? Awesome, great discussion. So now, another question we have, right, is I have this problem that now this instruction finishes at the write back, and the other instruction also want to write back at this time, right? So if that's the case, for write back, because I still have just single set of logic, this is the unfortunate case we still need to let the later instruction stall. Because unless you can provide another parallel logic for write back, right? So not all cases that we can optimize, right? So the basic idea is that you force the later instruction to stall, but there are some potential you can avoid that stall if you can modify your hardware logic in a way that you allow concurrent access of two instructions, like write first and read later. They have an agreement regarding how to time sharing this hardware unit, or you just make them a separate hardware unit, which is going to be more expensive, but that worth it. For example, the split L1 cache design. So here's a takeaway of the pipeline design. So the most efficient approach of addressing structural hazard is actually change the hardware design, because it's actually the structural hazard, right? So region file, we have seen that, and split cache design, we have seen that. Now, let's talk about another hazard, which is the control hazard. And remember, what we have about control hazard is because we have branch. So how often do we meet a branch? So first of all, this is the code that I have. I wrote a simple pieces of a code, right? So for this pieces of a code, it contains a for loop. And for the for loop, there is a loop control, and there is also an if-else statement. So the reason why I want to talk about this is because there is a terminology in branch that a lot of people get confused. And a lot of people, when they answer questions, they never pay attention to the comment that I wrote in the code. That is called branch taken and not taken. So the terminology here is, so like for example, this branch instruction, like JL, for each branch instruction, you could have two directions to go. One is to go to a target address, which, for example, is the label here. And the other is the next instruction. And the terminology of taken means that we are going to the branch target no matter what. That's no matter what is depending on, as long as a branch instruction goes to the target, it's called taken. If it goes to the next instruction, that's called not taken. And why do I want to say this? Because a lot of people, they think, whenever I see an if statement, when it's true, it should be taken. When it's false, it should be not taken. But in a lot of cases, that's actually not right. So one thing I want to say here is that, for example, like this one is actually taken when true, but I could also generate some code when taken is not true, right? So it's taken or not taken. It's based on if we are changing the direction or not. That's the terminology of branch taken or not taken. And how do you know this is whenever you see I put a comment here, when I say this statement is true, it's taken, then trust me, that means taken when it's true, right? If I say when false, it's not taken, trust me, that's false, it's not taken. But here is the big concept. Is taken or not taken simply means if we are changing the direction or not, rather than the real logical relationship of the previous statement. Question?
Yeah, so when you're saying when true, you're saying when it's true. Sorry, in the code that you have up there and not in the assembly that convicted.
No, so this is too difficult for you to tell. So what I would typically do is just let you know for this if statement, if its outcome is true, then it's taken.
And then if it was false, you would say taken and false.
Right. Yeah, because I like this class is not an assembly class. I never have the purpose wanting you to be writing assembly, right? I just want you to have a high level understanding about the assembly. So I don't want you to spend time doing that. All right. So so now let's talk a little bit about why we want to specifically caring about the branch performance. So first of all, right, if you look at the branch, right, it's actually stopping us from fetching, right? So whenever you cannot fetch the next instruction, right, whenever you cannot fetch the instruction, your pipeline will not be able to make a progress. And the thing is that when are we going to know where to fetch? Is actually after we execute this branch instruction, and then we will be able to know the target address to fetch, right? So as you can see, if you draw the pipeline, you have to almost wait as long as the latency of an instruction before you can fetch the next instruction, which is really slow, right? So here's the idea that we have. So if we cannot know what instruction to fetch, right? Well, this is pretty much like what happened during your midterm, right? If you don't really know the answer of a multiple choice question, and you know that I'm a nice guy, I don't give you penalty on like random guess, what you would do. Just make a guess, right? So this is pretty much that, right? So that's what our processor would do. If I don't know what's the next instruction to fetch, I would just guess an instruction, right? Because without guessing, I would just idle there. But if I guess it right, I can actually execute the instruction earlier, fetch an instruction earlier, potentially improve the performance, right? So to be honest, and what if I guess wrong? I just use my hardware unit to flush the result before it's actually committed to a register file, right? So to be honest, what's good and bad about prediction? There's nothing bad about prediction, to be honest, right? Nothing to lose, right? So here's the thing. Modern processors, we implement an approach called branch predictor. Try to help us guess what's the right next instruction to execute, to fetch. So now you can imagine in our processor, in addition to the original logic, I also have a branch predictor, which will give us another input to the program counter. So whenever I figure out this instruction that I'm dealing with is a branch instruction, instead of taking the next instruction as the program counter, I would consult the branch predictor to see what's the right next instruction to talk about. So next lecture, we will start with the branch predictor. But before we leave the classroom, several things I want to talk about. First of all, we have reading quiz due this Thursday. Don't forget about that. And assignment 3 already released. And plan your time carefully. And one last thing, which I just got an email from the Trident Testing Center earlier during the lecture, so I haven't put it on here. So I, like a good thing about like computer-based tests is that I can skim, like take a look of what happened during the test, see how you guys are doing. And how many of you, well, I know many of you probably are not that well prepared, or you are not familiar with how we use the Trident Testing Center. So this is what I'm going to do. So first of all, next Monday, because I have a business meeting with Meta, because we are doing some VR related stuff, so I will be in Seattle, not here. But in the meantime, I want to give you guys a second chance.
Yes.
I want to give you guys the second chance.
Yes.
And here's what I'm going to do is for the second chance, it won't be the same problem as the first midterm. It's fair, right? And I would add 1 or 2 questions that's about this week. So you might still need to do a little bit of work. But pretty much the majority of the question will be from the first 2 weeks. And I will announce what is the available schedule, but pretty much on next Monday and Tuesday only. And if you are not satisfied, so first of all, this is not required. So if you are satisfied with your first midterm grade, you don't need to take that. But if you're not satisfied with your second midterm grade, and if you do a better job than your first one, I can take your second one instead of your first one. Question? I don't think so. Because there are still people doing the exam, right? Question?
I don't know if you would know, but so I know sometimes for the test they give you the results right away. Sometimes they wait a bit. You know, for this one, you get
I don't know, because for the test that I took, they always give me right away. Yeah, I think like because I do like take the practice exam before I send this to you. That's why I said I only need 13 minutes to finish the exam, right? And I always see the result after I submit it, right? Question?
Yeah, you said only the higher one gets taken, right? So
Yeah. Yeah, so if you really want to take twice, nothing to lose, like the branch prediction. But that's a good news that I will share with you, right? So hopefully you will feel less stressful, feel happy. I know like a lot of you take summer classes for a reason. I know you, okay, so typically people don't really encourage students to take multiple courses during the summertime, but I do appreciate you guys recognize that summer session as a good time to learn a lot of things. So, but I also understand, one thing that I want to say, I do encourage, well, one thing that I regretted a lot when I was an undergrad student is that I took too many courses concurrently. So some of the courses that I feel I can do better. So, but you already did this, so I won't say too much about that because that's a decision you already made. But I would rather have you like getting better outcome, right? So because the purpose that I'm here is to let you enjoy computer architecture, knowing this is something useful, rather than like being really harsh on you guys and saying that, oh yeah, you have to do this to ace the class. No, to be honest, I want to be really honest to you, right? What's the purpose of taking a class? Is in the future, if you need a problem that's related to this class, you know, okay, this is related to computer architecture, where can I find the answer, right? To be honest, like just I don't believe you guys would remember what is like structural hazard like just maybe 1 week later. Probably 10 minutes later, you will forget what is structural hazard. So asking you guys to memorize things is never my purpose, but at least go through this, and I want you to spend some time on this and enjoy this like this. All right, other than that, enjoy the rest of your day. If you are attending the lab class, that would be 5 p.m. Other than that, enjoy the rest of the day. I will see you tomorrow.